Hello, learners. Welcome back to the course Mastering in Computer Graphics from Pixel to Virtual Worlds. So, we are in the module 4. In the last session, we studied scanline method, depth sorting method, and BSP tree method. So, in this session, we'll be discussing area subdivision method, octree method, and raycasting method. So, these methods are widely used in computer graphics for efficient determining the surfaces which is visible to the viewer or not. So let's start. The first method is area subdivision method. So this method is based on the divide and conquer strategy. The fundamental idea is very simple. So instead of analyzing the entire viewing area at once, so the viewing region is repeatedly divided into smaller rectangular section. That is what the working principle of area subdivision method. For each section, the algorithm determines whether the visibility is can be decided immediately. With visibility cannot be determined, so the section subdivides further into smaller regions. I'm repeating, for each section, the algorithm decides whether the visibility decided immediately. If the visibility cannot determine, so the section subdivided into further smaller regions. So this process continues recursively until the visibility becomes clear. So, so this approach reduces the unnecessary calculation by focusing only on complicated areas of the image. So take out this, it's entire view of the visible area. So apply the test whether the area is subdivided or not. If it is visible, if it is for each section, the algorithm decides whether it is visible or not. If it is not able to determine, section is going to be subdivided into smaller subsection. Okay, so at every level we have to apply test. Otherwise, we have to divide the image. Divide the visibility area into subdivisions, subsections. Okay, while doing the divisions, so the area is having some surface relationship with the uh, visible area, where we are having in the four kinds of surface: surrounding surface, overlapping surface, inside surface, and outside surface. Surrounding is the surface which is completely enclosed the area. So check out this image. So the area which is completely enclosing the visible area, that's what surrounding. Next one is overlapping surface. The test surface is partially inside and partially outside. So this gray area is a test area which is partially inside and or partially outside. And third one is inside surface. So our inside our testing area, some part is completely inside my testing area. And check out the last one is actually outside surface. So this is the gray screen is my surface, and this object is completely outside the surface. So the area surface relationships given here. Okay, so when we have to stop the subdivision, so we are taking the entire image, entire visible area into subdivisions and so on and so forth, right, recursively. So when I have to stop, so the conditions are given, all the surfaces are completely outside the specified area. In that case, we no need to subdivide. If some cases, if there is only one overlapping surface or only one inside surface, in that case, you can apply the background color, and then you can do the surface can be removed or scanned and converted. In some time, so there is a single surrounding surface but no overlapping or inside surface. In this case, the area is filled with the color and surrounding surface. Okay, so based on some condition, we can stop the subdivision. So the same thing is given here. Whether the surface is completely outside the area, we can stop it. An area has only one inside and overlapping and surrounding surface, that also possible. And the area is as one surrounding surface that obscures all the other surfaces within the area's boundary. So in that case, we can stop the subdivision. Okay, and so that is what the subdivision method, how it works. So the advantages side, the area subdivision method is it reduces the visibility calculations, and suitable for scenes for containing large empty regions, and is efficient for certain types of complex images. And coming to the drawback side, the recursive subdivision can become expensive, and performance decreases when many objects overlapping, and large number of subdivisions may be require highly detailed scenes. Okay, so that is what the drawbacks of the area subdivision method. Let's move on to the next algorithm, octree method. So octree method is extension of spatial subdivision technique into three dimension actually. So in the previous one, area subdivision, we are having two dimensional. So the same is implemented in the three dimensional view. That's what the octree method. So here we are having surfaces towards the front of the viewer, which is 0 1 2 3. Consider this 8 octets are there, nodes are there. So 0 1 2 3 are in front of the viewer, and 4 5 6 7 is going to be in the back side of the viewer. Okay, so when with the numbering method, the nodes are representing the octants 0 1 2 3 4 5 6 on the entire region we can represent in the 8 areas. Okay, so that is what the octree method. So let us see the working of the octree method. So the algorithm begin with the large cube representing the entire scene, and the cube is recursively divided into smaller cubes. For example, if you take the front view, so it is going to be taken like this. Each subdivision continues until the cube contains only one object, or cube becomes sufficiently small. So this results a hierarchy structure which is called as octree. Okay, so during the rendering, the system examines the only the relevant octants are instead of processing the entire scene. So this significantly improves the efficiency. So this is how the octree method is actually working. Okay, and coming to the advantages of the octree method, uh, it provides a efficient spatial organization similar to area subdivision method. It reduces the number of visibility comparisons because of division subdivisions. It accelerates the rendering complex scenes. So in 3D modeling, collision detection, virtual reality, game development, in all these area, this octree is efficiently actually supporting. Though we are having advantages, we are having some limitations. So limitations are needs additional pre-processing time for every image we are taking, and memory consumption also increases with the if you are submitting the high definition images or objects. Okay, so that is what the octree method. So moving on to the next method, ray casting method. So the ray casting visibility, it's determines whether the object is visible at each pixel. So it's a image based. So the basic idea is inspired by geometric optics. Instead of processing the object first, the algorithm start from the viewer's point of view. So from the viewer point of view, it is for every pixel on the screen, an imaginary ray is projected onto the screen. From the object, the imaginary line is going to be projected every pixel on the screen. So the object intersects the ray, the first becomes the visible object. So when we are projecting the from the scene to the object, which object is intersecting, that's going to be displayed onto the screen. So this technique is particularly effective for the scenes containing the curved surfaces such as the spheres. Let us move on to the working of ray casting. So at the step number one, we have to generate a viewing ray, imaginary line. Step number two, trace the ray onto the scene. And third step, we have to calculate the intersection between the ray and the objects. So as we saw seeing in the image, we have to project a line onto the object. So if it is intersect, so we have to find out the nearest intersection point. Okay, and display the color of the nearest visible surface. So that is the step number 5. So this process should be repeated for every pixel in the image. Okay, so the result is an accurate visibility result. Okay, When comparing with the depth buffer and raycasting method is actually pixels are processed first in raycasting, whereas in depth buffer, surfaces are processed first. Okay, in depth buffer method, depth value calculated for each pixel, whereas here all the surfaces are intersected by the ray are examined. Okay, that is the raycasting method. Sometime you may confuse with the ray casting and the ray tracing. So ray casting is trace one ray per pixel. So you have to project a one ray per pixel, find the nearest intersection point that is going to be visible one. In ray tracing is you will be tracing multiple rays and simulate the reflections, refractions, produces the realistic lighting effect. That is different. Ray tracing is different. Ray casting is different. You can check out this one, ray casting and ray trace. So for lighting and all, reflection and all, ray tracing is very much useful. But whereas ray casting is only one single ray onto the object. So coming to the advantages part of the ray casting, so it provides, as I told already, it provides a accurate visibility decision and handle the curved surface, especially spheres, uh, clearly, and it also produces the realistic images suitable for the geometric scenes. So that is what about the ray casting method for visible surface reduction. In this session, we discussed the algorithm, area subdivision, octree, octree method, and the third one is ray casting method. Oh, thank you for watching. So next session we'll be discussing the rest of the three algorithms. Thank you all. Uh, Hello everyone. Welcome back to the course Mastering in Computer Graphics from Pixel to Virtual Worlds. So we are in the module 4 visible surface detection methods, and in today's session we'll be covering the uh, last three algorithms for visible surface detection: curved surface visibility, wireframe visibility method, and found some functions in visibility detections using OpenGL. And so far, we were studied several visible surface reduction algorithms such as backface culling, depth buffer, Z buffer, scan line, A buffer, depth sorting, ray casting, BSP tree. So these methods primarily for polygon objects. However, many real-world objects contain curved surfaces like spheres, cylinders, cones. If you take an automobile part, you can see this kind of curved surfaces, even in mechanical components. So in today's lecture, in this session, we will be focusing on handling the visibility for such a curved surfaces by using these three algorithms. Okay. So first approach will be the curved surface. So let us start. So visibility approaches for curved objects by the four method. For three methods, already we saw the ray casting, octree method, polygon mesh approximation. So this ray casting is already we saw. So projecting a ray uh, from screen pixel to the object. So which nearest intersection will be taken out. That is what we discussed. And second approach is octree method. So dividing the hierarchical spatial division, subdivisions of an image. And third is polygon mesh is actually the curved surface is divided into many small polygons. So we call that dividing the polygons into small polygon called tessellation. Okay, so after tessellation, a traditional visibility algorithm can be applied, maybe Z buffer or scan line or depth sorting, anything. So this is the general approach for visibility approaches for curved surfaces. Let us see in terms of algorithms. So first one is first algorithm is that's what we say, right? So curved surfaces representing the curved surfaces by using any one of this method. So here. Um, Before visibility calculations, we have to represent the surface in the curved surfaces. The first one is implicit form, representing the surface into XYZ. a function of f of x y z equal to 0. A sphere can be represented in like x cube plus x square plus y square plus z square equal to 0. So that is one way. And second one is parametric form. So in a parametric form, the b plane and b surfaces are generally used to represent the curved surfaces. And third is actually explicit method. So here the surface can be expressed in terms of the height z equal to f of x comma y. So this representation often used in terrain modeling or height maps, contour maps. So in that area it is very useful. So different representations are suitable for different applications. So implicit form, parametric form, or explicit surfaces. Out of this, the next method is quadric surface. Quadric surface, a special category of curved surface is called quadric. So those are all spheres, ellipsoids, cylinders, cones. So these surfaces have some algebraic equations. So because of their mathematical simplicity, they are frequently used in the mechanical design, automobile design, molecular design, industrial simulations, and even many engineering graphics applications. So these are all uh, frequently used. Okay. And next representation is surface contour plots. So another way is actually visual to visualize the curved surfaces. This surface contour plot. Contour plot represents the points having the height information. Yeah, I think you may have noticed in contour maps in geography. In computer graphics, contour plots used to represent terrain visualization, scientific data representation, engineering simulations, and in medical imaging. So instead of displaying the entire surface, so we'll be having the contour lines representing the height informations in the images. So these contour lines can be projected onto the viewing plane. So that is what surface contours. And we'll have a visibility test for contour curves. For each pixel, when a contour curves are displayed, so hidden portions must be removed. So to perform the visibility test, we will be having two values: y minimum, the lowest visible point, that is what y minimum, and y max is the highest visible point. Okay. So if the range is hidden, so don't plot the point. If it falls outside the range, then it is visible, you can plot that point onto the surface. Okay. So if it is lies between y minimum and y maximum, so it is hidden, so we no need to plot it. If it is outside the range of x minimum, y minimum, y maximum, so definitely it may be visible, you can plot that point. So this is the technique, efficient technique, allows hidden line removal for the contour plots. Okay. So next is a wireframe method, wireframe visibility method. And here the wireframe model represents an object using uh, only edges of the object. Okay. So instead of displaying the surface, only lines and boundaries of the objects can be shown as a wireframes. So the visibility determination of wireframe models is known as wireframe visibility, visible line detection, and the hidden line removal. So the objective to display only the edges that are visible to the viewer, while the removing the hidden part or hidden edges. So this improves the clarity and makes the engineering drawings easier to interpret. Okay, that is what a wireframe visibility method. And you can adapt many algorithms for hidden removal in the wireframe method. So you can use backface culling. So you can apply that algorithm here for removing the hidden surfaces or hidden thing. And also you can use a depth sort. That's a painter algorithm. So you can paint the back and front. Okay. And draw the objects from back to front, and hidden edges are automatically covered by the nearer objects. Okay. And the area subdivision method, so dividing the object into boundaries. And the scanline method, so intersection of one line. So you can use for any of this algorithm and adapt it, modify it, and you can use it for the in a wireframe method, we can the hidden surfaces can be detected and hidden by using any of this algorithm in a wireframe method. Sorry. So next thing is wireframe depth queuing algorithm. So when viewing complex wireframe model, depth perception is very difficult. To address this problem, so we can apply the depth queuing algorithm. So depth queuing is nothing but varies the brightness of the object according to the distance from the viewer. Okay, so that is what the logic. So if the closer objects are very brighter and the distance objects are uh, very dim or appear very dim, so this actually mimics the human visual perceptions and provides a better sense of depth. Okay, as a result, the 3D structures become easier to understand by using the depth queuing algorithm. Okay, so the depth can be calculated by this formula: d max minus d divided by d max minus d minimum, and d mins are the are the values, intensity values. Okay, and next we'll move on to the visibility detection functions. So actually, the functions are implemented in OpenGL. So in modern graphics applications, uses the libraries from the OpenGL. OpenGL provides a built-in function for visibility determination, and the function support backways removal, depth buffer visibility testing, and hidden surface or line removal, calculating the depth queue calculation. So instead of implementing algorithm from scratch, the programmers the game developers or whoever using it, they can use the built-in OpenGL functions and they can use it appropriately. So we have some list of algorithms, for example, GL enable. So it is using culling algorithm, and GL disable, GL cull face mode. So these are all used to enable and disable the back face culling method. And this is check out this one, GL clear. This algorithm actually clearing the depth buffer, and this GL enable disable of by the depth you can calculate the depth test by this function. And yeah, these are all some algorithms and its functionalities, sorry, built-in functions in OpenGL for visible surface detection function, which means the algorithms, the functions are utilizing the adapting the existing methods from I told you, right? So backpace method, depth sorting, painter, the existing algorithms can be adapted to implement the hidden surface in a in the model by the OpenGL. And next function is check out this one, GL polygon mode. So this GL polygon mode is actually displays the objects as a wireframe. Okay, and check out this one, fog. GL enable fog is actually creates a depth based fading effect. That's what GL enable, GL fog I, and even GL fog G. Okay. And in this session, we discussed the curved surfaces, representing the curved surfaces, and contour visibility, wireframe visibility models, depth queuing calculations, and some of the visibility function by using OpenGL. So that is what about in this session. Thank you all.